All right, so this is my favorite probably and also the most challenging concept maybe of all of organic chemistry one. I'm not sure, but it's something that you can all do. You just have to work at it a little bit. And essentially what's going on is we're still talking about E2 reactions, but it turns out that the stereochemistry really matters. We have this starting material and these are two different stereogenic centers. So this is a chiral molecule, and if we pull off this proton in the E2 reaction, we're going to generate the double bond here, which would be a di-substituted alkene. That's going to be a tri-substituted alkene. It would have that, and that be its three substituents. And that's going to be the most stable product because it's tri-substituted versus if we pulled off the proton from here, it would be mono-substituted. So that's something that I think people are really good at, saying like, okay, we're going to have a more substituted alkene. That's easy. But the issue is we have two different options for that tri-substituted alkene. These are diastereomers of each other. And it turns out that this molecule is only going to make one of these two. So the question is, how do we know if this molecule is going to make that molecule or if this molecule is going to make that molecule? And I think what you're going to find is that it's pretty straightforward to figure out the way, but it's a lot of steps. We have to use Newman projections. We have to potentially rotate the molecule a little bit. So it's steps, but we will be able to get there. Okay, so those steps really, the first thing that we have to recognize is that elimination reactions occur at the fastest rate when the electrons forming the new alkene add directly to the backside of the halogen. So just like SN2 chemistry, backside attack inverts that stereochemistry. Why did it have to add to the backside of the halogen? That's because that's where that anti-bonding orbital was. So essentially, the carbon-hydrogen electrons want to add to the backside of the leaving group. So how can we visualize that? And what we will try to do is use Newman projections to visualize what that backside of the carbon-halogen is. So let me bring up a model of this molecule. So I built a model right here, and you can see that the bromine is red here. It's going back, so it's wedged. It's dashed. Sorry, it's dashed. It's a dashed bond up there, so it is going away from you on the model. This CH3 is a dashed bond, so it is also going away from you on the model. And what we need to do is we're going to rotate this a little bit to show that the hydrogen here is directly on the back side of this carbon-bromine bond. So essentially, all I'm doing here is I'm going to take the molecule as it's drawn up there, and I'm just going to rotate it like this. So it's just the slightest rotation, but essentially I'm showing that this carbon-hydrogen bond here is on the back face of this carbon-bromine bond there. So we're just redrawing the molecule a little bit. So I'm just going to do this little loop to indicate that we're redrawing. Redraw. And this CH was coming out at us. That's in the plane now. And when we move that into the plane, that pops this CH2, CH3 out. So I'm going to do a wedge here to CH2, CH3. And then that CH3 is now rotated down like this. And we rotated the whole thing, so that also put the carbon-bromine into the plane. And when that happened, the carbon CH3 bond went back, and this H is wedged now. So all we did was rotated the molecule. We see that the carbon-bromine bond, I'm going to move it over here actually. It's hard to do the model with the screen as well. But the carbon-bromine bond, oh, here we go. This is better. Is it? No. It's like mirror image. Okay, yeah, so the carbon-bromine bond is in the plane of the board, and that means that this CH3 is going back just like it is up on the screen. Here's that CH. The CH2, CH3 is coming out toward you. That's why it's a wedge up on the screen. And this CH3 is going away from you. You can't really see it because it's being blocked by this CH2, CH3. So we're in the right plane now. And what we're going to do now is we're going to look at this as if it was a Newman projection. And that's going to show that this bromine that I'm holding now, I'm holding the bromine, is directly in the same plane as this hydrogen here. Yeah, there we go. So yeah, we're essentially looking at this with a Newman projection now. So our Newman projection is going to be looking at it right here. And you have a Newman projection skeleton on the bottom of your note page, but it's actually coming from the other side on your note page, so I'm going to switch this around. So you can do it either direction, but just because of how I have the notes, I'm switching it around to looking from this side. So when we look at this side, the H is by my forehead. The CH2, CH3 is wedged, so it's coming out toward that camera. And then the CH3 is going into its dash, so it's going into the board. And then when I look at the other side, the bromine is going down near my chin. So we got the bromine down there. The H is wedged, so it's coming toward you guys. And then the other CH3 is dashed, so it's also going that direction. So here's our Newman projection. It shows that the H and the Br are in the same plane. And like we said at the beginning, elimination reactions occur at the fastest rate when electrons forming the new alkene are directly to the back side of the halogen. So the halogen's right here, that hydrogen is directly behind it. So what I have in this box, I'm also going to box in over here. So those are all in the same box. This wedged CH2, CH3 is with the wedged H, CH2, CH3, H. And this dash CH3 is with the other dash CH3. They're both dashes. They're both going the same direction. And again, I want to show that with the model. So we have what we have on the board. Now you can see it in the model. I'm going to look at the camera. Here we go. This will do it. Yeah, so we have the H coming at you in the front. It's in the same plane as the bromine right here. And then all of these groups, the CH2, CH3s right here, and everything makes sense. So, so that's where everything is. And essentially we're in that favorable conformation. The H is 180 degrees from that Br minus, and this is called an anti-periplanar arrangement of atoms. So this is an anti-periplanar arrangement of atoms. Let's break down that term. Anti, when we learned about butane conformations, was when the CH3s were on the opposite side. So essentially here we have the bromine on the opposite side of the hydrogen. That's what we're referring to as anti. And then periplanar just means it's all in the same plane. So how does this help us? Well, if this is where the alkene is going to be formed, and it is, this is where the alkene is going to be formed, right in that plane, then this stuff is going to be on one side of the alkene, and this stuff is going to be on the other side of the alkene. So we have the alkene that's being formed. So I'm just going to draw an alkene. And essentially I'm going to draw a dotted line through it. The CH3s are going to be on one side of that dotted line. So there's a CH3 and a CH3 on one side of that dotted line. On the other side of that dotted line, we have a CH2 CH3 and an H. So that is the product that we are going to have. So which does this match up with? Is this that product or is it that product? Well, if we draw that same dotted line through these alkenes, and this alkene, the CH3, is on the same side as the CH3 here. This CH2 CH3 is on the same side as that H. So this is the product. This doesn't form at all. So how did we do this again? We did this by taking the starting material, drawing a Newman projection, and making sure that H and the Br are on the opposite sides. And I also want to point out that we didn't necessarily have to do that. We can recognize that they're all in the same plane if none of those bonds are wedges or dashes. And essentially, that's what we have here. And then essentially the wedges were CH2, CH3, and H, right? This is the wedge, CH2, CH3. The other wedge was to the H. So they're going to be on the same side, just like we said here. They're on one side of the alkene. The dashes were a CH3 and a CH3. They're going to be on the other side of the alkene, just like they are over here. So then you just do your alkene, you draw your dotted line, and you put the groups where they're supposed to be. So this is kind of the process of figuring out whether we're going to make this stereoisomer or that stereoisomer. You have to kind of use these pieces that we've been developing through organic chemistry throughout the semester. So we're going to see more examples of that, and we're going to see a little bit more description of these conformations in a minute. All right, so one other thing to point out is that there's another Newman projection setup on your note packet, and essentially what I'm doing is I'm showing another reactive conformation. And what I said at the beginning, the elimination reactions occurs at the fastest rate when the electrons form the new alkene are added directly to the back side. That's from this anti-periplanar arrangement. But it turns out that if the hydrogen is actually on the same side as the bromine, so if they are directly on top of each other, that's also a reactive conformation, but it's a less stable reactive conformation, so it doesn't usually ever work really. But essentially we can get to that conformation if we just rotate 180 degrees from this Newman projection. So we're going to keep the front stuff the same, so the hydrogen's in the same spot, the CH2, CH3, and the CH3. And what we did is we're taking that bromine and we're rotating it 180 degrees. So now the bromine is eclipsing with the hydrogen. This H rotated over there. And this CH3 rotated 180 degrees over there. So this is a different reactive conformation. It can also do that E2 reaction. It's called the syn periplanar conformation. And like I said, it can do an E2 reaction, but it's going to be very high energy because everything's eclipsing. We know that things don't like to be eclipsed. They like to be staggered. That makes them more stable. Let's fill in some blanks. I'm going to write some more stuff, so I'm going to take a minute. All right, so we're still filling in those blanks on your course notes, but essentially anti-periplanar is the low energy. So low energy, what does that mean? That means stable. and productive. So we'll put that in parentheses, stable, productive. It produces product. Conformation for E2 reaction. So we have to find that anti-periplanar conformation. Once we do, we can figure out what product was made. Syn-periplanar is the high energy, unproductive or non-productive conformation for E2 reaction. So theoretically, this could still produce product. If it did, it would actually produce that product. But because everything's eclipsing, it is a less stable conformation, and it is not productive in this type of E2 reaction. So that's what goes in those blanks. The other thing that is on your course notes page is it says that acyclic alkyl halides can produce blank via E2 reactions. So that we're just filling in what's that versus that. So they can produce a single diastereomer. These would be diastereomers of each other. So that's the last blank on your course notes page. Acyclic alkyl halides can produce single diastereomers in E2 reactions. So yeah, more on that soon.